Linear programming is a mathematical technique that was developed to deal with optimization problems. In a typical optimization problem, our goal would either be to maximize profit or minimize cost, or occasionally we would maximize other variables, such as the number of people that are helped or the number of supplies that can be allocated to a certain situation. This technique was developed in the 40s by George Dantzig, and his problem was one of allocating supplies for the Air Force, and the goal was to minimize the total cost. So in this video, we'll talk about some of the basics of linear programming, and then go through an example of the process and how this works in a typical situation. So in a common type of application, we would be trying to allocate limited resources among competing activities in an optimal way. So obviously, the maximum profit would be unlimited, or the minimum cost would be nothing, but occasionally these constraints of the problem, the limited resources or different people groups that are wanting those resources, will prevent you from having the maximum profit or a minimal cost. So when we talk about a maximum, we're meaning as large as possible, but with the understanding that that's not that does have a limit on it in the context of a real situation. The phrase linear programming refers to both the type of functions and then also the method in which we're carrying out this mathematical technique. Right, so linear refers to linear equations, so you won't be using any quadratics or any other different type of complicated function. These are fairly basic, just linear equations or lines. And then programming refers more to planning activities to obtain the optimal result. It doesn't have anything to do with computer programming or anything like that. All right, some basic vocabulary. The constraints of the problem are equations or inequalities that represent restrictions on resources or conditions that need to be met in the problem. So some examples of constraints would be the limited number of hours in a work week, the fact that we cannot produce less than 0 products, if time was limited that was available in a factory or a plant, or if you could only hire a certain number of employees, or for instance, if your resources were limited, if you only had so much steel available, or if a bakery had a maximum amount of flour that could be purchased, something like that. Then the objective function is the function which describes the objective. So for example, if we're maximizing profit, then we would write a function to represent what profit is. If we're minimizing cost, we would write a function to represent the cost. The region of feasible solutions is going to be all of the points on a graph which represent solutions to the objective function that satisfy all the constraints of the problem. So your functions, profit or cost, these are going to be dependent on a couple variables x and y. Right? And then we'll want to graph that function, and we would be interested to know what values of x and y can give us a maximum profit or a minimal cost, but also still meet all of the conditions that we've put on this problem in the form of constraints. Right? So in many cases you're going to end up with kind of like a little boxed in region on your graph, and we're looking to see what values of x and y in here give us the maximum profit. And then finally a vertex. The vertexes, or the vertices, are the corner points of the feasible region. So in this case in this example that I've drawn, we've got 4 vertices, one at each corner. Okay, the process of linear programming. So here are the steps, and we'll refer back to these. Right? In the first step, you want to identify the variables in the problem. What is it that you need to find? So for these situations, we'll be dealing with 2 variables, x and y. Otherwise, if we had 3 or only 1, we wouldn't be able to graph this problem using equations of lines. Okay, then we'll write an objective function, in many cases profit or cost. Then write the restrictions or constraints of the problem as inequalities. So you'll be using less than or equal to, greater than or equal to, etc. Okay? All right, then we'll graph the system of linear inequalities. So we're going to be graphing lots of different equations, inequalities, right? And then the feasible region, right? You know that each one of these would be shaded on one side or the other, and then you should end up with kind of a boxed-in region where those would all overlap. And then finally, we'll test the vertices in the objective function to see which one yields an optimal value. All right, so we would find these points, identify them, and see which one gives us the greatest profit or the minimal cost. Okay, all of this will probably be more clear if we go through an example. So let's do example 1, and this is from your textbook, Mathematical Ideas, page 443. The Smartsky company makes 2 products, DVD recorders and MP3 players. Each DVD recorder gives a profit of $3, while each MP3 player gives a profit of $7. The company must manufacture at least 1 DVD recorder per day to satisfy one of its customers, but no more than 5 because of production problems. Also, the number of MP3 players produced cannot exceed 6 per day. As a further requirement, the number of DVD recorders cannot exceed the number of MP3 players. How many of each should the company manufacture in order to obtain the maximum profit? Okay, so this is a lengthy problem, and in real life it might not have even been phrased this nicely. You might have a complicated problem that's not even set up to be put into this sort of a technique. All right, so this one's been set up to give you everything that you need, but it is still a lot of information. So what we need to do now is go back and identify some of the key points in this problem that we need. So let's start with identifying the variables. What is it that you need to find? So in most of these, you can kind of look at the last sentence, and that should tell you what it is that you need to find, and then we'll just choose variables to represent those things. So in this case, we're asked how many of each means DVD recorders and MP3 players, should the company manufacture in order to obtain the maximum profit. Alright, so we have 2 things, a number of DVD recorders and MP3 players. So we're going to let those be our X and our Y. X is DVD recorders, Y is MP3 players. Then part B, write an objective function. So again, that last sentence does give you your objective, and that is to obtain the maximum profit. So we're going to write a function that represents profit, and it should be in terms of X and Y. Everything we'll write now will be in terms of those 2 variables. Alright, so we know that profit is a combination of the money that's made from each of these 2 items, and we're told that DVD recorders give a profit of $3, MP3 players give a profit of $7. So your profit would be 3x, $3 times each of the DVD recorders, plus 7y, $7 from each of the MP3 players. Alright, step C, write the constraints as linear inequalities. So now we're going back through and looking for keywords such as is more than, is less than, cannot exceed, cannot be under, we need a minimum or a maximum, things like that. Alright, and then I can also kind of cross out the information that I've already used. So the Smartsky company makes 2 products. We know this. I can cross that first sentence out. I've used everything in there. The second sentence is telling me what the profit is, and I've already used that. Okay. Then the last sentence, that's just telling me what I'm supposed to be doing or maximizing. So I'm done with that. And then everything in the middle would give me my constraints. So the company needs to manufacture at least 1 DVD recorder per day. So DVD recorders, that's your X. And that needs to be at least 1 per day. Right. And then also no more than 5. So X, the DVD recorders, needs to be less than or equal to 5. Now I can write this as 2 separate inequalities, but I can also write this as a compound one. Right? So basically what I'm saying here, if x is greater than or equal to 1 or less than or equal to 5, I'm basically just saying that x needs to be sandwiched between those 2. So x is between 1 and 5. Right? So you can write it in either of those 2 ways. And then the number of MP3 players produced cannot exceed 6 per day. So y must be less than or equal to 6. And then as a further requirement, the number of DVD recorders, that's X, cannot exceed the number of MP3 players, so X has to be less than or equal to Y. Alright, that's all of the constraints that we've been given in this problem, but there are always two more that are implied and not usually stated. So think about what X and Y represent, and certainly we could make as many recorders or MP3 players as we want, assuming that fits with the other constraints we've been given. However, it would not be possible to produce less than 0 of those things. So we also have two understood constraints. Both X and Y must be greater than 0, or equal to 0. Okay, so we have a total of 4 constraints. We've got this one, this one, this one, and this one. Oh, sorry, 5. One more. Okay, and then in the next step, we need to graph the feasible region, and I've just asked you to describe the steps you took to graph this. You don't need to submit your graph, but if you choose to, then you can certainly just submit the image of the graph instead of describing how you graphed it. Right, so it's up to you, one option or the other. Okay, so if we're graphing this, I'll go through those steps with you, and then you would basically just describe everything that we're doing in this step. Alright, so the feasible region, if you look back at the vocabulary, this is kind of the region that is the overlap between all of those different constraints. So what I need to do next is to graph each of these constraints. So I have X is between 1 and 5. I have Y is less than or equal to 6. I have X is less than or equal to Y. And then I have the fact that my two variables are positive. All right, so notice I've already drawn only the first quadrant of this graph, only the portion where X and Y are positive. So we're kind of ignoring these other sections of your graph since X and Y must both be positive. Okay, so the first one, X is greater than or equal to 1 and less than or equal to 5. Right, so this line would represent where X is 1, and this line would represent where X is 5. Right, so then if X is between those two, then we're just sort of shading in this region here. All right, now there are a couple ways you could do this. You can shade as you go for each of these and then look for the overlap, or sometimes what I like to do is just draw arrows so that I don't have too much shading, and I just want to remind myself that I'm shading to the right of one line and to the left of the other. All right, and then Y must be, your next one, Y must be less than or equal to 6. So that would be the line here, horizontal line. And then if Y is less than or equal to 6, I'd be shading below that line. Okay, and you can go based on the direction of the inequality symbol, or you could always do your test point 0, 0. 0 is less than or equal to 6, so I know I would shade the side with 0. Okay, and then I have one more, X is less than or equal to Y. Right, I can also kind of flip this around and treat this as Y is greater than or equal to X. And then if you remember how to graph inequalities, we would start by looking at the boundary line, Y equals X, and then we would decide where to shade from there. So this one is set up for you. You could use a couple points that make the equation true, or you could use your slope and your intercept. So right now this is Y equals 1x plus 0, so I could think of this as a line that has an intercept at 0 and then a slope of 1, so it would just be going up 1 over 1 to find other points on that line. Alright, and then notice I could also just think about what types of points would make this equation true, and it would be any points where X and Y are equal, so 3, 3, 4, 4, 5, 5, etc., etc. And then I'll just put a line through those points. Okay, and then I also need to consider where I shade on this one. I can't use 0, 0 as a test point because that's actually on the line, so I'll choose something different. I'll choose maybe this point here, maybe 3, 0. Okay, and then in my original inequality, that would give me 0 is greater than or equal to 3. And that's false, so I would be shading the other side of that line or above it. Okay, so now I just need to look at all of these arrows and determine where the shading would overlap. So I've got to be between these two. I have to be below this one and above this one. Right, so that's going to be this region here, and that's boxed in. Okay, so my next step, I need to list the vertices of that region. So as I'm graphing, I want to try to figure out what those points are, and most of these you should be able to see that they cross kind of evenly right on one of the integer marks, but if not, then you would need to do a couple other techniques. But in this case, we can just see from the graph what those vertices are. Oops. Okay, so I have this one, this one, this one, and this one. And that looks like it's 1, 1, okay, 5, 1, 2, 3, 4, 5, 5, 5. Okay, right above that I have 5, 6. And then I also have 1, 6 as well. Okay, so 1, 1, 1, 6, 5, 5, 5, 6. Oops. Five, 1, 5, 6. Okay, so this is the cool part of this technique. All of those points that are shaded in orange, all of those satisfy the constraints of the problem, and any one of those could give us the maximum profit. However, we have a theorem that's been proved that tells us that the maximum profit or the minimum cost, whatever that optimal value is, will always occur at one of the vertices of this region. So this is an important theorem because it does save us a lot of work. There really would be no way to test every single one of those points that's in the orange region, because you're also thinking about fractions and decimals, and there are an infinite number of points squeezed in there. So obviously we wouldn't be able to check all of them, and we would be left with a little bit of uncertainty as to whether or not we actually did find the maximum value. However, this theorem does give us reassurance that one of these 4 points that we've identified will be the maximum value for this problem. So that's the reason why we're only testing those 4 points. And that's the next step. So let me make a chart here. And what I want to do is just test each of these in the objective function. So if you look back to that problem where we wrote the objective function, right, that's profit equals 3x plus 7y. Alright. So I just need to determine what the profit is at each of these points. Okay, so I'll plug these in. The profit for 1, 1 would be 3 times 1 plus 7 times 1, or 10. 1, 6 gives me 3 plus 42, or 45. 5, 1 gives me 15 plus 7, or 22. And 5, 6 gives me 15 and 42, or 57. Okay, so it looks like in this case that the maximum profit can be found at that vertex 5, 6. And then finally we can interpret this, what this actually means in the context of the problem. So 5, 6, right, that's an X and a Y, and we said that X was DVD recorders and Y was MP3 players. So this means in order to obtain the maximum profit, this manufacturer should produce 5 DVD recorders and 6 MP3 players. Right? And when that happens, the maximum profit will be $57. Alright, so that's a complete example. In the next video, I will do a second example with you, going through the same process again in a different situation.